Hello students, Mr. Williams here to tell you about speed and velocity today. Pretty short video coming up. Just to remind you, yesterday, or in our last time that we talked about displacement and distance and the difference between those two values. And now we're going to talk about speed and velocity, which rely on our differences in distance and displacement. Let's see what we mean by that. So what is speed? We use this term pretty frequently in everyday life. Well, speed is just an expression of how a position changes over time. Speed is how we want to quantify how quickly an object changes its position. Speed is a scalar quantity, and we talked yesterday about scalar and vectors, meaning they only have magnitude. Magnitude is just a size or an amount. It is just our term for size or an amount. It is just how big a number is. And speed is a big number. We can say that a car has a speed of, 20 miles per hour. Or a snail has a speed of 2 centimeters per minute. And neither of those have a direction associated with them, but they do have a value, 20 and 2, and we measure that value in some known unit. That's what speed really is, how quickly an object changes its position. Velocity is very similar to speed, but it describes the rate of change of displacement. Rate of change is going to be a term we see often. Rate of change of displacement. It is a vector because displacement is a vector, meaning it has magnitude and direction. So an example of a velocity might be 4 meters per second north. Or how about our velocity is negative 2 miles per hour. And that's enough right there. Negative 2 defines a direction just like north does. Because speed can't actually be a negative. Think about that. Could you ever be moving at a negative speed? Well, no, because you can either be at 0 speed or you can be moving. You can be more than 0, but you can't have negative speed. You could move backwards, but that is a direction. And so that has to do with velocity. Speed itself can never be negative. So speed, let's just review, quantifies how fast an object is moving. It is a distance divided by a time. We measure it in meters per second for an SI unit, and that's usually what we want to go with. It is always positive, never negative. An average is not the same as instantaneous. An average is over time. An instantaneous speed, think about that word. Instantaneous is at a specific time. So think about how a car initially, let's say, is at rest, VI equals 0, and then sometime later, he lost his hood. Sometimes later, he is moving at, 20 meters per second. And that's his instantaneous speed right here, instant. Well, over time, like he wasn't always moving at 20 because nothing is ever moving at the same speed forever. It wasn't moving at all. And then we started to speed up, and then we had an average in between there of over time. Or like, let's say, and we can see that in our equation here, speed is distance over time. This is really giving us average, A-V-E-R, average speed. It's just distance divided by time. Well, if I wanted to solve or rearrange this equation and think, how would we do that? I could just multiply both sides by time here. Multiply both sides by t. We would get that distance is speed times time. And then if I wanted to solve from time, we could also do that. Again, rearranging my equation. Just imagine speed is equal to d over t. Well, if I multiply both sides by t, what happens is I get d is s times t. And then what if I wanted time? Well, I could divide both sides by s, and that's exactly what we see down here, distance divided by speed. And so these are a few equations we can use to calculate certain values, and we'll use them in just a minute. But first, velocity. So velocity, similar to speed, is rate of motion and direction associated with it. Also measured in meters per second, both are. But velocity is a vector, and it is important that we remember that because the sign then gives us our direction. And like we said before, we're going to stick with one dimension, meaning we're going to be moving in a straight line. So 0, let's say 5 and -5. Well, we have a positive direction and a negative direction. So if I have a car or an object and it's moving a certain direction, positive or negative, if I say the motion is 5 meters per second, well, that is inherently positive 5. It's moving forwards at 5 meters per second. Or if I tell you that a person over here is moving backwards at negative 2 meters per second, well, I know backwards is negative, and that's why we have that. So velocity is displacement over time. Very similar. And we have a couple other equations to get that, and really they are the same, but because we are displacement is delta x over t, we're going to go ahead and write these in variable form rather than writing them out like we did for speed. And we get average velocity is just change in position over change in time. If we were to give you a certain exact position, so say we start at 0 and then we go to 20 meters per second, and that was at a time of 0 and 10 seconds passed by and it took us to get there. Well, easy, we just do 20. In these cases we had zeros, but they don't have to start at 0. We could have subtracted by anything in these cases. That would come out to be 2 over 10 or 20 over 10, which is 2. Notice this does give us an average velocity. AV is standing for average here. For the rest of this unit, I'm just going to write it as just V for our velocity, and that is just delta x over t. Notice we drop the delta in this case because most of the time t is just like the time that has passed for an object to happen. We usually do not give times at 5 seconds we started and then at 20 seconds it ended. It's more likely that we just tell you that it is 15 seconds that has passed. But delta x is our specific term for displacement. Displacement is delta x, and we're going to keep that in all of those equations. Okay, so let's do a couple quick questions. When will speed and velocity always be the same? So think about that. We have speed is distance over time. Velocity is displacement over time. What's a situation when they will be the same? Well, they will always be the same if distance is equal to displacement. And when will they be different? Well, if distance is not equal to displacement. And that makes a lot of sense, right? So speed is just d over t, and velocity is delta x over t. Whoops, that was a d. Delta x over t. Well then, if delta x and d, distance, are the same, then we get the same thing. But if they are not, then we will get different values. So let's do a couple practice problems here. A cow runs down its 40-yard pasture in 5 seconds. What is its speed in meters per second? In meters per second. So go ahead and pause the video and see if you can get this answer. So first thing we want to do is we want to know what is its speed. Well, speed, we have an equation, it's just distance over time. And I'm told that it runs down its 40-yard pasture in 5 seconds. Well, that gives me a speed of 40 divided by 5, gives me 8 yards per second. So I'm done. Or am I? We were asked, what is the speed in meters per second? I have a speed down here in yards per second. How could I possibly change my answer to give me what I want? Well, we need to use unit conversions. Remember all those things we learned last week? We are going to continue to use them. So I need to convert between yards to meters. And if I look up that conversion, I can find it right here. 1 meter is equal to 1.09 yards. They're very close, but not exactly the same. And notice what happens, yards cancels. I will be left with meters per second when I do 8 divided by 1.09, and I get 7.3. I'm just going to round that to 7.3. Meters per second is my final answer to question 1. 7.3 meters per second. All right, question 2. During a storm, you see a flash of lightning, and 3.5 seconds later, you hear the sound of thunder. Given that sound travels at 340 meters per second, how far away did the lightning strike? Go ahead and pause the video and see if you can get this on your own. All right, so let's identify what we know here. We see 2 numbers, and this is always a great practice to go through in any problem. underline what numbers we got. And let's figure out what do we know and what are we asking for. So I'm given 3.5 seconds. That's a time. I'm also given that sound travels at 340 meters per second, that is a speed. I'm going to call it V for velocity. And I want to know how far away I'm trying to solve for delta x. Do I have a relationship between these three variables? Well, let's just go back. I do. I see delta x is just V times t. That can solve for distance if we travel at a constant velocity, what sound does. So delta x is just going to be equal to 340 times 3.5. And why don't we go ahead and double check while we're doing it here. Make sure that our units cancel. 340, that is meters per second. And I'm going to multiply that times 3.5 seconds. Well, notice we have meters per second. And then seconds in the numerator, those seconds will cancel. And what is my unit out is going to be meters, which is what I want because it's a displacement. So I do 3.5 times 340, and I get 1,190 meters. It's how far that lightning, that the sound had traveled in the time that it took lightning to strike. And this is actually something you can do during a lightning storm. The longer it takes for thunder to hit after lightning, the farther away that lightning struck. Okay, let's see if we can do this challenge problem. An athlete sprints 50 meters in 4 seconds, stops, then walks slowly back to the starting line in 40 seconds. For the direction of the sprint is taken to be positive, what is the average velocity for the sprint, walking, and round trip sections of the trip? So let's draw it out. Anytime we have really any physics problem, drawing is always helpful just to help us picture what's going on. An athlete sprints 50 meters forwards. Starts over here on the left, sprints 50 meters forward, and does that in 4 seconds. Stops. We'll even draw that out here. And then my nice red goes here, and this takes 4 seconds. Well, then they walk back to where they had started, and that takes 40 seconds. And I want, if the direction of the sprint is taken to be positive, which I did, I'm going to say this is positive and this way is negative. I want to know the velocity of the sprint, walking, and round trip section. So let's figure that out. So V for my sprint. Well, what's my displacement? Well, my displacement was positive 50, and I'm going to write that positive here just to remind us that we moved in our positive direction 50 meters, and that took 4 seconds to happen. 50 divided by 4 is 12.5 meters per second. And that's it. That's how fast they move. The sprinter had moved during the first 4 seconds. Then they turn around. So then our velocity of our walk is going to be, miss my L there. Walk is going to be, again, we went 50 meters, but this time we went backwards during the walk. And that took 40 seconds. That comes out to be negative 1.25 meters per second. How about B of the round trip? What's that come out to be? Well, that velocity, we'll think of the round trip. What was our total displacement? We went forwards 50, then we went backwards 50. What was our total displacement? We ended up where we started. So our total displacement was 0. And it took 44 seconds to get to 0, but doesn't matter. We still get 0 meters per second for our final displacement. And there we see